Alright, this is 3.1 continued part 2. We're going to do another example, pick up where we left off on identifying the sign of f of x that helps us graph and sketch this. Alright, so here's our example. Let f of x equal 9x minus x cubed. So let's first put some information about it. The degree is 3. The leading coefficient here is a -1, right? Yeah, and your constant is 0. Right? There's no constant here. Your y-intercepts. Well, if we plug 0 in for x, we obviously see that our y-intercept is 0. So next we need to find our x-intercepts, which will require a little bit of work. So let's deal with this function. Right? I would factor this. I'd first pull out a negative x, right? Which would make it an x squared minus 9. Yeah, x squared minus 9. Yeah, and then that'll come out to negative x plus 3, x minus 3. So our x-intercepts or our zeros are 0, 3, and negative 3. Alright? So, do your number line. You got a 0, you got a negative 3, you got a positive 3. Here's your 4 regions. So let's put our information about region number 1. Well, it goes from negative infinity to negative 3. Region number 2 goes from negative 3 to 0. Region 3 goes from 0 to positive 3. And region 4 goes from positive 3 to positive infinity. Alright, so let's figure out what signs these things have. So we'll pick a number in between negative infinity and negative 3. I'm going to say x equals negative 4. You can pick whichever number you prefer. Right? Plugging negative 4 back into our original function, we see that we get a positive 100. So that's a positive sign. The y values are positive in this range. A value in between negative 3 and 0, I would say just negative 1 is simplest. That comes out to a negative 8, which is obviously a negative. Values in between 0 and 3, let x equal 1. And that comes out to a positive 8, which is positive. And then values in between 3 and positive infinity, x equals negative 4, comes out to a negative 28. That's negative. Now we're ready to sketch our graph based on all the information that we have. We can find our min-maxes, we can find our turning points, etc., etc. So we know the y-intercept is 0. We know our x-intercept is 0, or x-intercepts are 0. We'll say this is negative 3. We'll say this is positive 3. So we've got an x-intercept here, here, and here. But we know in the range from negative infinity to negative 3, the y values are positive, which means it has to be coming down like this, right? We know in between negative 3 and 0, the y values have to be negative, which means it dips down like this. We don't really know exactly how far it goes. We can plug numbers in to find out. And then 0 to 3 is positive, which means it has to curve back up, go through 0, because that's our y-intercept and an x-intercept, and become positive again, and then obviously it goes back down like this. So we know our graph looks something like that. We could find exact numbers, but recognize this tells us we have 2 turning points, which is our min and our max. Alright? We'll do one more example. It's a little slightly different, give you something different to look at, and that'll wrap up this section. Alright, so last example. Let f of x equal x to the 4th minus 4x cubed plus 3x squared. Alright, so the information we have right now is this degree 4. The leading coefficient is 1. Our constant is 0. Y-intercepts are 0. And we're going to do some work to find our x-intercepts. All right. Well, let's factor this. Factor out an x squared. You get an x squared minus 4x plus 3. That factors very nicely into an x minus 1, x minus 3. So this tells you that your x-intercepts are 0, 1, and positive 3. All right. So let's do our number line. Here's 0, here's 1, there's 3. So here's your first region, your second region, third region, and fourth region. Okay? So, first region goes from negative infinity to 0. Second region goes from 0 to 1. Third region goes from 1 to 3. And your fourth region goes from 3 to a positive infinity. Same thing that we've been doing, plug in a number that's in this range. Obviously, x equals negative 1 is the easiest. That gives you a positive 8. So that's a positive sign. I chose to plug in x equals a half in this range here. That came out to 5/16, which again is positive. For this range here, I plugged in x equals 2, which became a negative 4, which is our first negative. And then this range here, I just plugged in x equals 4 and came up with, I think it was 48, which again is positive. What this tells us is we really only have one negative in our signs, which is interesting. So now we're ready to graph it. Let me erase this. We need a little bit more room so we can see this graph. All right. So let's put it on the graph. What do we know so far? Well, we know the y-intercept is 0. We know our x-intercepts are 0, 1, and 3. So we know these are the points where the graph is going to cross the x-axis. We know it's of degree 4. That's really all we know. So from negative infinity to 0, we know it has to be a positive sign. So the y's are positive coming down like this until it hits 0. In between 0 and 1, it's still positive. But what I want you to notice is 8 is a lot bigger than 5/16, which tells me as these numbers are coming down, let's say this is y equals 1 mark here, there has to be probably a little bit of a loop here. So where the half, x equals a half mark is probably a 5/16 there. Right? I made it bigger to exaggerate the loop. But the decreasing of these numbers tell us that there's got to be a decreasing here, and then probably a slight increase, and then continue to go down. In between 1 and 3, we know it's got to be negative. So here's 1, here's 3, so it's coming down like this. But we know it has to loop back up because it has to go back through positive 3. And so this is the rough sketch of the graph. What's interesting is, here's your max, here's your min. Alright? So we have 2 turning points. Right? It goes from positive to negative and then back to positive again. So positive to negative and then back to positive again. So again, we get 2 turning points, and we could verify what our min and maxes actually were. Alright, last thing in this lesson. I mentioned this early in the year when you guys probably weren't listening. In behavior. In behavior. Alright? Let me rewrite that for you. Behavior. In behavior. Alright? So really what this boils down to is, what does the graph look like? What does f look like at the far right and left points. In other words, what are these graphs doing way out here? Are they bending back? Are they flattening out? What's going on with them? End behavior. So here's some tricks for end behavior. Let me erase this stuff real quick so we've got enough room to write this stuff out. This will help you in the future. It will also help you when you're trying to sketch a graph and get an idea of what a graph looks like. All right? So if f is an nth degree polynomial with leading coefficient a sub n. So remember, in the form of a polynomial, the standard form, a sub n is the leading coefficient. Then here's the rules. Number one, if n is even and a sub n is greater than 0, then the end behavior of the graph is going to look something like this. It's going to be in the first and second quadrants. All right? If n is even and a sub n is less than 0, then the graph is going to look something like the end points of the graph, or the end behavior of the graph is going to look something like this. So it'll finish in the third and fourth quadrants. All right? What about if n is odd? So if n is odd and a sub n is greater than 0, then the graph, the endpoints, the end behavior of the graph will be in your first and third quadrant. And if n is odd and a sub n is less than 0, then your end behavior is going to be in your second and fourth quadrants. All right, so the end behavior of a graph combined with the identifying signs of a graph, combined with the degree, the leading coefficients, and all the intercepts, can really make it easy to sketch what a function looks like. All right, so that pretty much sums it up for 3.1, chapter 3, section 1. We'll work on some homework in class. Good luck.